All right, this is going to serve as a review for the AP exam for thermodynamics. So we're going to go through and learn all the key concepts for thermodynamics for you to be successful on the AP exam. All right, first thing, in thermodynamics, the thing that we care about the most is figuring out whether or not a process is going to be spontaneous or not. The idea of spontaneity means that you're not adding any extra energy, like a ball rolling down a hill is example of spontaneous. A ball rolling up a hill would be non-spontaneous. So we're basically not adding any extra stimulus or energy, make something spontaneous. Key things to keep in mind, endo and exothermic. In any thermochemistry, we talk about a system as being a chemical reaction. If something is exothermic, it means that energy is exiting the system. It correlates with a negative sign for delta H, because we use a lot of delta H values, or delta H is enthalpy, so it's a negative delta H value. If energy flows into a system, we say that is endothermic, and we give it a delta H value as positive. During chemical reactions and an exothermic reaction, we just talked about how energy is released. New bonds are more stable whenever you form an exothermic reaction. Endothermic energy is required to input into the system. New bonds are always less stable in an endothermic reaction. Okay, so heat flowing in, the process is endothermic. What does it mean for the surroundings? Whenever you have an endothermic reaction, it actually makes the surroundings cooler or colder, and the temperature drops. That's key for when you're reading questions and they're asking you whether, and you haven't identified something, what type of reaction something is. When you see the temperature drop of the surroundings, that means that energy is flowing in, and it's an endothermic reaction. Likewise, if you have an exothermic reaction, heat is leaving the system. Well, if energy is leaving the system, it's exothermic. What does that mean for the surroundings? The temperature increases, or it gets hotter. So the surroundings are going to get hotter, it feels warmer, temperature increases. That's one way of kind of interpreting whether something's exo or endothermic, by looking at what happens to the surroundings. All right, so we talked about that. Delta H is positive when it's endothermic. Delta is negative when it's exothermic. One thing you have to be able to do is look at a graph and determine whether it's exo or endothermic. You have the reactants here, products here in this graph, looks like that. Whenever the products are lower than the reactants, it's called a downhill reaction, or it's exothermic, meaning the delta H value is negative. You can actually find the value for delta H by taking the difference between the reactant line and the product line will actually be the energy that is released in the reaction from reactant to products. Products are more stable. Talked about that already. Endothermic reaction. Notice the reactants are here. You reach a higher level with the products. The delta H value can always be found by taking the distance between the products and the reactants, which is going to correlate to this amount of change right there. So from there to there is going to be the delta H for the reaction. We say this is endothermic because it's gaining energy in the reaction coordinate diagram. All right, one thing you have to remember is heat is a conversion factor. We learned this before. We have a delta H value that sits at the end of the reaction. Technically, it can be a conversion factor. You could take 12.8 grams of H2 gas, convert it using molar mass. 2 grams of H2 is equal to 1 mole of H2. They're asking what would the heat change be? I take the coefficient of H2, which happens to be 1, and the delta H value to make a conversion factor, which is 1 mole of H2 is equal to negative 184.6 kilojoules. They expect you to be able to do this on an exam. Usually it's in the free response section. They'd have you do a calculation where you have to calculate the amount of heat. All you have to do is change the substance, whatever it is, to moles. Once you have moles, you get the heat to mole ratio from the equation here. The value that sits here relates back to either one of these using the mole ratios or the coefficients. There are 3 ways to find delta H, and you have to be able to find all of them. We learned this when we went through in chapter 6. First way is a heat of formation table, which I'm going to show you in a little bit. Second way is Hess's law. We actually did a lab right before spring break. That's where you basically do a Price is Right style. You flip the reactions to match a target reaction when you add them together. Last one is bonds broken minus bonds formed. You would be expected in the free response section and the multiple choice section to be able to find delta H using any of these methods. So if you look here, we learned this with equation flipping. If you look, they ask you the difference in delta H between this reaction and this target reaction right there. Well, if you look, the value basically, O3 is on the same side, so you don't have to change the sign. So the sign is still going to be positive 285.4. The difference between this reaction and this reaction, that value has a value of 2. This one has a coefficient of 1. So to get the new delta H value, all I have to do is divide by 2. So whatever you do to the coefficients of a reaction to make it match the target is what you're going to do to the delta H value. Heat equation. This is where we're actually how we find heat in a laboratory. We're actually going to use this to calculate the Q or the heat in our lab. It's just mass of the substance, and usually when we do calorimetry, it's water. Mass of the water. Delta T is the final minus initial temperature, and CSP is the specific heat of a substance. You can either find it or you can look it up, or you know it. Like, for example, water you should know is 4.184. You throw these three values in there, you get Q is always going to be spit out in joules. It's kind of the basis for our lab. So when we do our lab calculation, when you get back, you'll be able to see that pretty easily. One way to find delta H is enthalpy of formation. Kind of looks like this, has a delta H value, and has a little subscript F for formation. There's tables that list the values of heat of formation. So you see like this table right here, lists a whole bunch of values. You can look them up. They're only compounds. Key thing to remember on the exam is if something is an element, it does not have a delta H value. So the delta H value is going to be 0 because it doesn't take any energy to form elements, only compounds. So here's a bigger table right here. You know, it's a whole bunch of different values. You have to pay attention to state matters. Water as a gas, water as a liquid. If you notice there's differences, so pay close attention to that when you're grabbing values. Here's an example of a delta H problem. Remember, heat of reaction is solved by products. Sum the values, that's what summation means, minus the sum of the reactants will give me my heat of formation, or my delta H for the reaction. So what do? Well, I take a reaction like this, and I look up the values. So for example, CH4, that's negative 74.81. That comes from the table right here. I look up CH4, negative 74.1, or 0.81. It's a compound, so it has a value. It is a reactant, so I'm going to put it over here, 3 times the negative 74.81. I also have water as a liquid. I go back to the table right there. Water as a liquid is negative 285.8. I make sure to include the coefficient. So I have negative 285.8 right there. Coefficient of water is 2. So I multiply by that 2. Last one is CO2. If you look back at the table, it's negative 393.5. 393.5 times 1. I get all my reactants. I would sum those up. That's what the brackets mean. I get a value for that. Then I go to the products because it's products minus reactants. I look up CO as a gas. If you go back, CO as a gas is negative 110.5. I go back over here. I take 4 times negative 110.5. Because the coefficient, remember, you got to pay attention to the coefficients when you do this. The coefficient there is 4, so I multiply that. This is 8 times 0. The reason why is that is elemental. A lot of times on the exam when they have you do heat of formation, they just simply won't tell you it's 0. They expect you to know that the value should be 0. You can't look it up on a table. They wouldn't give it to you. All right, next thing, delta S. Delta S is also a key part of thermodynamics. It means entropy, which is a measure of disorder of a system. Disorder is favored over order in nature. We tend to go towards disorder. So positive delta S value tends to be spontaneous. A negative delta S value is non-spontaneous. There's 2 ways to find delta S. You can do it by inspection. That's where you use the SLG rule, or the number of moles, to figure out whether or not the sign for delta S, or you can actually calculate it, which we'll get to a little bit later. I'll show you that a little later. So if we look right here, processes that are spontaneous in one direction are obviously non-spontaneous in the other direction. So if you look right here, remember if delta S is positive, we say that entropy is increasing and it correlates to being spontaneous. If delta S is negative, we say that entropy is decreasing. It is related to being non-spontaneous. Here's our SLG rule. As you go from a solid to a liquid, delta S increases. As you go from a liquid to a gas, delta S increases. By the way, aqueous also belongs down here. If you make something aqueous, it's supposed to be a Q actually, right there. So delta S goes positive that way. If you go from right to left, we say delta S value is negative. So delta S value is negative, we use the SLG rule. That's the first thing you should always look for when you look at a chemical reaction. If there are only gases present, you can't obviously use the SLG rule because there's not different states. That's where the number of molecules or moles of a gas increases during a chemical reaction. So the number of moles increases from left to right, we say delta S is positive. If it goes larger moles on the left-hand side than the right-hand side, we say delta S is negative. So if you only have gases present, you count the number of moles. Like here, I have 1 mole of gaseous product on the reactant, 1 mole of gaseous reactants, 2 moles of gaseous product. I would say the value for delta S, the sign for delta S actually, is positive. Okay, so if we look right here, first thing I look at is the state. I have a liquid, I have a gas. I can use the SLG rule. I know going from a liquid to a gas, my sign for delta S, is going to be positive using the SLG rule. If I look right here, I have a gas and a gas. So then I have to use number of moles. Well, I have 1 mole on this side of gas, 2 moles of gases on this side. My sign for delta S is going to be positive. Next one, C. Gas, 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 gas. 2 moles on the, 2 moles on the left, 2 moles on the right. There you can't predict the delta S value. We say there's no change. Finally, solid on the left, solid on the right, so those kind of cancel out. But then I have a gas. So I ignore the solid to solid, but solid to a gas means that my delta S value will be positive. Next one. I start here, solid to a gas. My delta S value is going to be positive. Solid, gas, solid, gas, solid. So essentially I'm going from a gas to a solid. My delta S value would be negative. If you look here, gas, 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 and a solid, my delta S value is going to be negative. Last one, gas, gas, gas. I have 3 moles on the reactant side, 2 moles on the product side. My delta S value would be negative. That's how you do delta S by inspection. Okay, the more complex a molecule is, the greater entropy or the greater delta S value. If you compare the two same molecules, they have to be at the same temperature because a higher temperature means greater entropy. If you look here, these are at the same temperature and they're the same state of matter. So that's the first key thing. Then it goes down to the more atoms you have in your molecule, the greater the entropy is going to be. I have 5 total atoms in this molecule right here. This molecule, I have 8 total atoms. Therefore, this one would have the greater entropy. All right. Last thing I'll highlight really quick on this episode is how do we find delta S calculation style? Same way we did delta H, it's products using stoichiometric coefficients minus the reactants. When they've been summed, you can calculate delta S instead of doing it by inspection. So products minus reactants, sum of each, will give you delta S. You look at a problem right here. Here's my equation. Note when you're doing delta S is in joules. When we do delta H, it's in kilojoules. Everything has a delta H value. Everything has a delta S value, unlike delta H, which elements don't. If you notice here, oxygen is 205, 186, 213, 188. So what do I start with? I start with my products. I'm going to take my products, my CO2, which has a coefficient of 1, So it's going to be 1 basically times 213. Water has a coefficient of 2, so I'm going to say 2 times 188. That will be my product side. CH4 has a coefficient of 1, so 1 times that value, 2 times the O2 value, which is that. It looks like this when you're all said and done. You basically use the stoichiometric coefficients here and here. I get a value for the products. So all you're doing is multiplying and adding. I get 591.08. The reactants, I use the coefficients times the values from the table. I get 596.3. Then I subtract the two values. I get negative 5.2. So it's much more accurate to actually calculate the value for delta S because then you get the sign. Okay, I'm going to stop right